The, the topic is pore pressure prediction in water flooded reservoirs. We all know that pore pressure prediction is very important in oil and gas business. But in general, all the attention in pore pressure prediction is focused on exploratory wells, but also in developed wells. When we are drilling a well in a development setting, there are lots of uncertainties. Often they are very much ignored. In this presentation, really, we'll only start, we'll capture only a part of it, and we'll specifically deal with the problems of pore pressure prediction in a water flooded reservoir. So just before starting, let me give me a brief introduction about myself. I'm a petroleum engineer with about 4 decades of experience. I have worked in Oil India Limited in India, BG Group, Shell International Exploration and Production, and Petroleum Development Oman. Last 20 years of my life, I have worked internationally. While in Shell and PDO, I was the technical authority in reservoir engineering, and I have a master's degree in petroleum engineering. I've taken a number of courses, technical courses in PDO and Shell. I was in charge of graduate development program in Shell and PDO. I've published number of technical papers, and currently I am a freelance reservoir engineer. I teach in Indian universities as guest lecturer, conduct workshop. I give consultancy to small operators, and I do independent project reviews, and I run number of online courses through PEA and also some face-to-face training in different E&P companies. That's my brief introduction. Coming to this, first let me tell you what's the session objective, why we have really met. Our objective is very straightforward: to develop an understanding of the issues that need to be considered while predicting pore pressure for drilling a development well in a reservoir that is being water flooded. That is, in one sentence, I have written that. It means if there is a well, development well, that we are drilling, in a reservoir in which water flooding is going on, then what are the issues we should consider in predicting the pore pressure prediction for that well? That's the whole objective, session objectives. So just for some people who might not have worked in water flooding, just one introductory slide. What we do in water flooding, we inject water, either in the oil zone or in the aquifer. And my objective is to recover more oil. So if we inject water, and the objective of injecting water is simply to recover more oil and increase the value of the asset, this is water flooding. This is the current definition of water flooding. Earlier, people used to distinguish between water flooding and water injection for pressure maintenance. But nowadays, this distinction is not made, because we have realized that even though if we inject water in the aquifer with the primary purpose of maintaining reservoir pressure, there is an element of sweep very much present, which enhances the recovery. So that distinction between water injection for pressure maintenance and water flooding as such does not exist in modern petroleum engineering literature. Coming to the session roadmap, how will we proceed with this? First, there are a few slides to really tell you why pore pressure prediction is important. Next, we'll tell what needs to be done in pore pressure prediction, what exactly we need to do in pore pressure prediction. And then we come straight away to the topic and discuss what considerations we need to make for doing pore pressure prediction in a reservoir that is under water injection. And to bolster all the points that I'll be making, I'll give you 2 case examples. There are many, many case examples, but I'll give 2 case examples to illustrate this point. Coming to the first topic, why pore pressure prediction is important. See, pore pressure prediction, we call as PPP, is the most important HSSE, which is health, safety, security, and environment activity that any subsurface personnel is directly involved with in his professional life. A reservoir engineer usually works in the office, and he is not directly connected with many of the HSE things which a person who is working in the field is involved in. But pore pressure prediction is one such activity in which reservoir engineering plays a very important role. So it is a very critical element of process safety. Okay. Now, process safety means is very different from personal safety. The definition of process safety is that it is any incident, okay, which is unplanned or uncontrolled release of hazardous material. It can be toxic, it can be non-toxic, it can be flammable, it might not be flammable as well. For example, steam, hot condensate, nitrogen from a process. If you have uncontrolled flow of these things, we call this a process safety incident. A process safety incident can be very catastrophic. Some of the pictures are given. Okay, the very serious one, the rig blowout in Oklahoma, rig oil blowout in Turkmenistan, and the latest one, the Mocambo project in Gulf of Mexico of BP. I won't go and really discuss these things, why it happened and all that. That you can see more detail in YouTube, or you can search the web for these things. But pore pressure prediction is a very important element to avoid such process safety incidents. Now, the consequences of process safety incident can be many. It can be a fire or explosion. It can result in multiple fatalities. A lot of people might lose their lives. It can result in permanent disabilities. There can be major asset damage. In very extreme cases, your license to operate may be impacted. People will think the operator who is involved in doing this, he is no good really, he is not competent to operate. So license can be taken away. There can be prosecutions and fines. There can be disruption of production. There can be serious environmental damage, which usually happens with a process safety incident. And there can be a serious damage of reputation for the company. Okay, so process safety incident is something which is very serious. And pore pressure prediction is one of the things in which reservoir engineer is involved. Okay, and one of the objectives of doing a good pore pressure prediction is that we drill a safe well so that we can process safety incident. Next comes the question, okay, what do we need to do in pore pressure prediction? What it is all about? Pore pressure prediction is a very detailed topic. Okay, in this particular presentation, I'll be only touching one part of it. So pore pressure prediction is a key HSE activity for subsurface personnel. As I've told earlier, it is required for drilling of new wells, new development wells, any well intervention, or even well abandonment operations. So you need a very robust pore pressure prediction and also fracture gradient prediction for all these purposes, to drill new wells like producers, water injectors, disposal well, aquifer pump off wells, whatever be it. If you want to drill a well in a safe and cost-effective manner, we need a very robust pore pressure prediction. Now, what is the objective of pore pressure prediction? In pore pressure prediction, what we need to do, we need to provide an estimate of pore pressure in all porous and permeable formation from the surface to the total depth of the proposed well, irrespective of whether the zones are hydrocarbon bearing or not. That means if you are doing a pore pressure prediction from the surface to the target depth of the well, okay, wherever we expect to encounter a porous and permeable formation, irrespective of the content, fluid content of that formation, I need to give the predicted value of pore pressure before drilling any well. Now, this pore pressure prediction is always provided on the top of a formation. Now, question comes, why really it is on the top of a formation? That we'll discuss, I think, in the next slide. Now, this pore pressure prediction is used for two things. One, definitely well controlled during drilling via design of proper mud policy, and also for designing casing policy for a well. Coming to one point that you might be asking really, why pore pressure prediction is done always at the top of a porous and permeable zone. Let us suppose we are drilling this well and we have an impermeable bed at the top, which may be the cap rock. And this is a gas cap drive reservoir with an aquifer. So it's a combination drive reservoir. We have an oil zone, we have a gas zone, and we have an aquifer. And I have come over here, top of the zone. I need to predict the pressure, what will be the pressure at the top of this zone. If you look at this figure shows the local pore pressure gradient. Okay, it can be anything between 0.433 psi per feet to 0.5 psi feet per feet, or if you are doing in SI units, maybe 9.8 kPa per meter to maybe 11.5 kPa per meter. That sort of gradient will be there. This is a normal gradient. Now, see, I'm drilling a well. Here, I'll encounter the top of the formation in a gas zone. Now, the pressure over here, this is the free water level. Okay. The pressure at the top, when I drill a well, it will encounter the pressure in the gas. It will not encounter pressure in the water zone. Okay. Now, because of this pressure, my pressure over here will be higher in the gas zone. The pressure in the free water level for all the phases will be same. Over here, I have an oil gradient. Suppose I come over here, I look at this pressure. But if I come to the gas zone, I'm looking at a much higher pressure. In many of the situations, if your gas cap is only a few meters in thickness, this extra pressure may not be that significant. Okay, you might have a small kick. But suppose you are drilling to a formation which has a huge gas cap, maybe very thin oil column, but a huge gas cap, this pressure may be very, very significant. Now, if you don't take care of this, okay, this is known as a buoyancy effect. If you don't take care of this, you might get a very serious kick, and in the worst case, a blowout. That is why, because of this buoyancy effect, I have a pressure in the gas zone, which is higher than that of the normal aquifer, though this whole reservoir is purely normally pressured reservoir. That's why we always give the pressure at the top of any permeable zone. Coming to this is the standard plot. All of you might have seen. On the x-axis, we have pressure. On the y-axis, we have depth. This is a normal hydrostatic pressure. Normal hydrostatic pressure doesn't mean that it is 0.433 psi per feet or 9.8 kPa per meter. A normal hydrostatic pressure always means the pressure which reflects, okay, the pressure gradient which reflects the salinity and the temperature of the formation. It depends on that pressure. So pressure may be 10 kPa per meter in a very oil with low salinity, maybe 3000 ppm, but same water at the same pressure and temperature might have significantly higher gradient, maybe more than 11 kPa kPa per meter if you have maybe 200,000 salinity. So this hydrostatic pressure is always referenced with the in situ formation that we have. It is not with respect to really just distilled water or 0.433 psi per feet or 9.8 kPa per meter. This point is very, very important. Okay, so pressure is overpressured is always respect to the correct hydrostatic pressure using the correct gradient for that field. So this is my pore pressure, and this is my fracture pressure, and this is the lithostatic pressure. Okay, so my pore pressure, if it's overpressured, it will be more than hydrostatic, but it will always be less than fracture pressure, because if your pore pressure is greater than fracture pressure, then there is no way the fluid will be there. It will just escape. So technically, your pressure is always, okay, less than fracture pressure. Now, this is one example where we really use pore pressure prediction. I won't go into detail because all of you might be aware of this. This is my pore pressure prediction, which a RE has done for a development well. Usually in a development well, reservoir engineer is in charge of doing the pore pressure prediction. And this is the fracture pressure prediction, which is usually done by either petrophysicists or in large companies by the geomechanics team. Now, when you give this pore pressure prediction and this fracture pressure to the well engineering team, they always take a safety factor. Okay. What they do, they tell, okay, let me take a margin. This dotted line I'll take as the fracture pressure, and they'll take a line over here taking sufficient safety, and this is my pore pressure. Now, I start drilling a well. I take some fluid so that I can control the pore pressure, and I'm definitely much less than fracture pressure. This gradient I am using. As soon as I strike this point, okay, I can't go really, and I need one casing, otherwise my pore pressure will be larger than the fracture pressure. So you see one casing is there. Similarly, I go with this, I put another casing, I go with this, I put another casing. The point I want to make it is that there can be larger number of casing than whatever is really I've shown in the figure, because the choice of casing may be dictated by something else. But these are the minimum casing that we need in this particular situation based on pore pressure and fracture pressure considerations. Now coming to pore pressure prediction, we're coming to the subject as such. A subsurface system has a large number of uncertainties. Sometimes we think that there can be only uncertainties in an exploratory system, but any subsurface system is inherently filled with uncertainties. So since the system is inherently uncertain, it doesn't make much sense to give a single value of pressure. Okay, that means as soon as I give you a single value of pressure means it becomes a deterministic system. That means I know the value of pressure, but in a subsurface system, there will always be some uncertainty. So it is prudent to give a range of pressure that captures the uncertainties that we know. Okay, so we don't give really one single value of pressure. As a minimum, I'll give some expected value, I'll give a low value, and I give a high value. So why these uncertainties can be there in a development location? Because the uncertainties that can be there in any development well can be due to depth. At what particular depth we'll encounter the formation. What is the fluid fill? You might not know exactly to 100% certainty where is the gas oil contact, where is the oil water contact. You don't know 100% maybe somewhere whether it is filled with liquid, with gas or oil. The impact of water injection, which is the topic that we'll be dealing in detail, so I'm not talking about it. What is the degree of depletion? What is the lateral continuity? Whether there are communication through boundaries. Okay. And also the element of time-dependent variation of pressure. Okay, because in a dynamic situation, in a development well, maybe you have planned to drill a well in February 2024, but the well got delayed and you are drilling the well in October 2024. If a reservoir is under water injection, there may be changes in pressure. Okay, because there is a time-dependent element with it. Ideally, we need to give a range of pressure. This reflects all the underlying uncertainties. So in any pore pressure prediction, when you do on the top of each zone, we try to give minimum 3 values of pressure. One is the expected value, one is the high case, and one is the low case. Maybe we give a value which is P50, P90, and P10. Typically, as we do for the reserves, that's the minimum requirement. Now coming to the main topic really, because I am not delving on the entire pore pressure prediction and how the uncertainties come in and how we take into pressure, then really you have to run a course on pore pressure prediction, which might run for at least minimum of 16 to 20 hours. So we'll talk specifically on pore pressure prediction in a water flooded reservoir. See, first thing we need to appreciate is that major reservoirs in the world are under water flooding. Today, water flooding is the #1 recovery method in the world. 50% of the current production and 50% of the developed reserves in the world are all under water flood. Now, many of these reservoirs, okay, are being developed in a very small well spacing, especially if you are really developing a highly viscous oil. The only way of increasing recovery from a highly viscous oil may be infill drilling. So we reduce the well distance and water flooding simultaneously. Okay. So what we are seeing that the distance between two wells has come down significantly if you want to increase the recovery factor in a highly viscous oil reservoir. I have seen wells when I was working in Oman where the distance between two wells has come to as low as 43 meters. So there can be wells at a very, very shallow, very, very small spacing. Now, if there are number of producers and injectors in the neighborhood of a new well being drilled, now you put a new well for drilling. Maybe you're converting 5 spot to a 9 spot, you're completing existing pattern, whatever be the reason. If you're drilling a development well, this well will be impacted by all the producers and injectors nearby. And I now need to predict the pore pressure of this well in presence of all these producers and injectors. In many of the cases, based on our pore pressure prediction, okay, we may need to shut in a number of producers and injectors, okay, while the reservoir section of a new well is being drilled. So this is very much essential sometimes to avoid a kick or avoid a stuck pipe situation due to differential sticking. So this is the topic that we'll be talking today. So this example just shows a field from a Middle East. I'm calling it our field. You see, this field is being developed at a very small spacing. This red, the wells numbers written in red, they represent the producers, and the one in green, sorry, in blue, represent the injectors. Whenever this field, every year, okay, there was a drilling campaign in this field. Whenever there was a drilling campaign in this field, it was really a nightmare. Okay, we have done a pore pressure prediction. Okay, suddenly we find that we are getting a very severe kick and we are unable to really go on, continue to drill this well, and we have to shut in a number of injectors, okay, suddenly, or do something maybe beyond that. So this is an example of our field in Middle East when we are doing a waterflood development. We'll come to this in detail a bit later as a part of one of the case studies. Now, this is the main topic really, the pore pressure prediction in water flooded reservoirs, what we do really. So I need to predict the pressure at any point, okay, in the reservoir, okay, at a fixed distance from a producer of our injector. Okay. When I want to do this, I need a line source solution to the differential equation of fluid flow. See, petroleum reservoir engineering is really very simple. We solve the equations basically under two situations. One we call as constant terminal rate solution, and other is constant terminal pressure solution. What is constant terminal rate solution? A constant terminal rate solution is one in which a well is producing or injecting at a constant rate. I'm holding this rate constant, so I'm calling it a terminal. I'm holding the rate constant. Now, if the well is injecting at a constant rate or producing at a constant rate, what will be the pressure at any point I want to find out? This is known as a constant terminal rate solution. Opposite to that, we have a constant terminal pressure solution, which mainly deals with I'm maintaining a pressure at the oil water contact. In response to that pressure at oil water contact, how much of water will influx into this reservoir? So in this situation, if I want to predict a pressure at any point when I'll be drilling a well, okay, then I have to employ this line source solution. Why I call it line source? I call it line source means I approximate the well by a single point. If I approximate the well by a single point in the elevation or in the front view, it can be replicated by a line. That is I call a line source solution to differential equation. Then let us see, based on this line source solution, how do I decide which injector should shut in, how long it needs to be shut in, or which producers need to be shut in, and what's the duration of shut in. I won't really go into too much of mathematics, but in reservoir engineering, mathematics comes in really. It is not totally avoidable. So just for that, so I have a constant terminal rate solution. A well is producing at a constant rate, Q is constant. Then pressure, the flowing bottom hole pressure in this well passes through phases. I'll initially have a transition state and a late transition state, then a steady state. If I want to find the pressure at any point, okay, and any time, so I am writing the pressure P at a distance R at a time T, okay, Then this is the fundamental radial fluid diffusivity equation. All of you might be knowing 1 by r del del r del p del r, phi mu c by k del p del t. This is the radial diffusivity equation. This equation, like any other equation in the world, it has some underlying assumptions. The most important underlying assumption is one is a homogeneous reservoir. So we are looking at constant porosity, constant permeability, and the properties are not really isotropic, means properties are all same in all directions. And we are also assuming radial flow. So if this is the equation underlying my fluid flow, then the line source solution tells me PRT means pressure at a distance r at a time t is equal to pi, whatever is the normal pressure, minus q mu by 4 pi kh. This is an exponential integral from x equal to 5 mu crt by 4 kt to infinity e to the power minus s by s ds. This whole thing is known as an exponential integral. Okay, so I need this. I need to solve this equation to find the pressure. So delving a bit deep into this, what is this exponential integral all about? It might seem, wow, how will I find this, solve this EI function? This exponential integral is known as EI function. EI to the power, EI is a function of x, is from x to infinity e to the power minus s by s ds. It's pretty much simple. It might look intimidating. It is not. This is the graph of e to the power minus s. This is a graph of e to the power minus s. And this is the graph of 1 by s. This is a reciprocal function. Okay, so the graph is always, for reciprocal function, is a rectangular hyperbola. So if I want to multiply e to the power minus s by 1 by s, so that I get this function e to the power minus s by s, I get this graph. What this graph I'm doing, for a particular value of s, I'm finding what is e to the power minus s, I'm finding what by s, I'm multiplying, and I get this function. This is integrated between x to infinity. So if I want to find what is the value over here, okay, what is the value over here, I can find out. That means it is from s equal to x till infinity. That means from here to all the point till infinity. This curve becomes asymptotic to the x-axis as we move, and I can find the value of EIX, and this is the value of this EIX function. So this is how really using an EIX, I have to really solve this. Luckily, we don't have to really go and do all this. If your x value is very small, it can be easily proved mathematically that EIX is equal to ln x, logarithmic function, minus 0.5772, which is the Euler function. We call it minus log gamma x. This formula is only true if x is less than 0.01. You see, this is the graph we have drawn of EIX. Here, I have approximated it by minus log gamma x. You see, till this point in time, I can tell that EIX is equal to minus log gamma x. Means really, I did not bother. The EIX function can be really approximated by log gamma x function. This is very, very important. Why? Why it is very important? To think of pressure well test analysis. Suppose I am doing a build-up test. Suppose I am doing a drawdown test. There, in the same well, where I am really implementing any change of rate, same point I am trying to measure the pressure. So x is very, very small. So I don't need really EIX function. That is why you don't encounter any EIX function when you are doing really a build-up test or a drawdown test or pressure fall-off test. You are not encountering EIX function. But if I want to find pressure at a point which is at some distance from the well, such that this logarithmic gamma x assumption is no longer valid, then I have to use this EIX function. The most common example of this is any interference test. If you do an interference test, then you need to really use this EIX function. So let us look at it. What's the impact? This equation enables us to find the pressure at the target well location with one or more injectors continuing injection. Okay, and it can also help us if I shut in the pressure well for various duration, how my pressure will change. Okay, similarly, I can find out for a producer. Let me give two examples, okay, to put my point. This is a simple thing we have implemented in Microsoft Excel. Very simple to implement that really, that EIX function. This is a well, okay. This is a well, okay, which is really injecting. You see, your injection pressure is, your pressure is in kilopascal, and it's the distance from the well. So in the y-axis, I have pressure in kilopascal. I'm injecting at a very high pressure, more than 20,000 kPa, okay, and that this is the pressure profile of the well, normal pressure profile of the well. So you see, if I want to drill a well which is within 50 meters, in this particular case, I might encounter a very high value of pressure, though my reservoir pressure may be less than 10,000 kPa, maybe 8,000 kPa. But if I am really drilling a well at a 50-meter distance from the injector, my well will see a pressure of 12,000 kPa. Okay, but as we go away from the well, maybe 150 meter, 200 meter, you see, I'm really coming down to pressure which is very much lower, really. Okay, we are looking at the normal reservoir pressure, really. Okay. This is the source. So whenever we are doing, okay, a development location, I look at its distance from the injector. Okay, and I have this profile, injection profile, which I can generate. Knowing the distance from the injection well, I can know at a particular distance how much pressure I'll encounter. In this particular example, if I'm drilling a well 250 meters, which is, I don't know where it is coming.
Yes. Yes.
I am having some problem, but really I should be able to circumvent. So if I'm drilling a well, maybe 500 meters from this well, or even 300 meters from this well, it doesn't impact much. Just please remember one thing. This plot, this generation, assumes solution to the diffusivity equation that I have shown earlier, which assumes this equation, which is for a homogeneous reservoir and radial flow. It assumes those things. Okay. Similarly, but the biggest problem is that, okay, can we always go by this EI function to predict the pressure of a well? There can be situation, okay, where there exist some fractures. The fracture may be in natural fracture. The fracture may be an induced fracture which has happened due to injection over a period of time. If the well, okay, the producer and the injector, this is the producer and this is the injector, they connected by some fracture path, then the fundamental assumption of radial flow is no longer valid. Then we might have a linear flow, and pressure drop in a linear flow is much lower than as compared to that of a radial flow. So we can be really in deep trouble. Okay, we assume that there is radial flow and the well is connected by a fracture, and we can have a very serious problem in our pore pressure prediction. We'll come and see one real life example from the North Sea. This is one. Okay, this is another example. This is just the opposite. This is the case that we are having a producer. So, you know, most of the pressure drop in a well happens very close to the well because of the radial flow assumption. Here also, if I drill a well very close to a producer and I don't shut in that producer, I might encounter a very smaller, much smaller pressure. Like in this particular example, the pressure is coming around 7,500 kPa, though my reservoir pressure is 8,500 kPa. So there can be a problem. Okay, this can result in a problem of differential sticking. Just the opposite, because I'm predicting my reservoir pressure is actually much lower than what I normally have. Okay, so my overbalance increases. This can result in differential sticking. So it is not that only water injector creates a problem. Even a producer can create a problem potentially. Okay. In addition to these things, in a water-flooded reservoir, you might sometimes think that you know everything. Okay, but we have serious vertical conformance issues. You might have very serious vertical conformance issues. In this particular example, this is my producer and this is my injector. And this is just a schematic really. I'll go and show you a real life example. These are the various formations A, B, C, D, E. You see, what happens? A, it is neither completed in the producer or injectors. Now, suppose in this particular formation D, I am constantly injecting. Okay. And this producer is actually perforated in C. Maybe the person who was responsible for doing the correlation can, for very good reason, think that this and this are same. So this is a very serious situation. This zone D, this reservoir D, is getting overpressure because we are injecting for a very long time. Okay, and we are thinking that it is a part of C. Now, when I drill a well over here, I might get a pressure which is very, very high. And this has happened many, many times. I'll get a pressure very, very high because there's a problem of correlation. We are injecting, pressure over here is built up a lot, but we do our forecast based on normal pressure. And this is not at all drain. I get a pressure which is very, very high. These are some of the impacts of really vertical conformance. I'll give you a real life example. This is a real well from a well number. I'm calling it XXX from B field. Okay. These reservoirs, they contain very high viscous oil and they're all thin sands, as you could see from here. And such thin sand doesn't make it economic really to produce just from one zone. So we are really producing, there is commingled production and injection. You see over here, the first, this one, which gives the pressure in kPa of the various formation, and this is an MDT data. So this gives you the mobility. Okay. So you see this zone, same well, pressure is 11,399 kPa. Okay. This zone, you can see the mobility is low, may not, the reservoir quality is not good. It hasn't produced much, pressure is very high. But over here, you see, this is a zone which is so much depleted, looking at 2,600, 3,600, 3,072, 4,500. But we have zones like 11,399, 11,179. So whenever we are really drilling a well, going in a field where there is commingled production and injection from number of thin zones, you face a lot of really problems in really predicting the pore pressure because you don't know really the well that you will be drilling, which are the formations you will encounter and what exactly will be their pressure. Coming to the case studies really. Okay, I'll just show you two of them. This is a field X in North Sea offshore. Okay. In this particular field, okay, we are really doing an workover. And let me come to the figure really. You can see the RDLs of 3 wells. This is the well which is injecting in these zones. And this is the well which was a producer and we wanted to do some workover in this well. Okay. And this is another producer in which this particular zone has not developed much. They had good hold on pressure. The pressures were 7,000 psi in this well. Okay. Based on that, a reservoir engineer has done pore pressure prediction and he has given P15, P50, P85 or whatever, P10, P50, P90 pressures as 6,000, 5,500 and 5,160 psi. That is the pore pressure prediction he made based on this. How he made this prediction? By using EIX solution. He knows what is the distance. He knows what is the pressure over here, 7,000 psi. He knows what is the injection rate in this well. He knows what is the porosity, permeability, etc. between this well. He assumes radial flow, use the EIX function, and he has given 3 values of pressure: 6,900 as 6,000 as the high case, 5,500 as the base case, and 5,160 as the low case. So people went to go and do work over in this well. So, but one of the key uncertainties in this well was what was the degree of connectivity A, B, and C. The geological interpretation shows there is no major barrier between well and B, A and B. They went ahead, they calculated based on the base pressure and they were ready for the high case. But there was a very high permeability streak between this well and this well. So we cannot really do this. This is really like a fracture, very high permeability streak. and this well were nearly directly connected. So when they actually encountered was a pressure of not 6,000 kPa, but a pressure of 6,900 kPa, which is significantly higher than even the high case estimate. So this being an offshore well, they had to really do a lot of things to control the well. They stopped injection in well A, and then they went ahead and they back produced the well. They back produced the injector, trying to lower the reservoir pressure as much as possible. At the same time, in the well, in the workover well, they weighed up the mud. All these things, they could put the well under control, but 1 week of lead time was wasted. You can assume that in a field like North Sea, if 1 week of rig time is wasted, then what can be the financial impact of this? So lesson learned from this is that first, though pore pressure prediction in many companies is the responsibility in a development well, is the responsibility of reservoir engineer, but actually it's a very multidisciplinary thing, because the reservoir engineer is not the best guy maybe to find out really what is the connectivity to in many cases. If you have doubt, and you are in a water flooded situation and you don't know really whether there are fractures are there or not, you're having doubts, and you know there can be high permeability streak, somebody saying there may not be high permeability streak, you are on the defensive side. You go and shut in the injector, because you lose much less money by doing that than if you have an NPT in a non-productive time in a drilling rig. So this is the lesson we learned from this well. Next one, okay, this is a well which really I personally worked in, and I had a lot of nightmares. It contains very high viscous oil, maybe close to 100 centipoise. It is developed using pattern well water flood, and the only way of increasing production from this well that the field development plan says, you go and drill more wells, reduce the well spacing, and go and increase your injection. So infill drilling and water injection is the way to increase recovery. So whenever we are drilling a campaign, okay, drilling campaign in this field, always a number of injectors need to be shut in for doing this drilling here. And this reservoir, okay, the drive mechanism is very strongly due to really water injection. As soon as you shut in the injectors, within a few days, you find that your field production is coming down a lot. So often managers are very reluctant to shut in so large number of wells. Okay, they find, can you find some way of really minimize this shutting really? So this is the field I have shown earlier, and this is the reservoir description logs. As you can find out, so difficult it is, so many zones are there, so many small reservoirs, and mostly we are doing commingled production and commingled injection. Whenever we had operations in this well, it was nightmare for the people. Sometimes you cannot sleep at night. Your people will come, operation to tell you that I have shut in the wells which you have told, but still I am unable to control the well, I am getting kicked. Then you really go and see which well you need to shut in. So after detailed analysis of everything, we worked out a scheme really for each of the wells that we are drilling. This is a new well that we will be drilling in a particular well. This is the location. Okay, then we are telling which are the injectors that need to be shut in before really we drill the reservoir section. So we give this, and in some of the cases, even shutting in may not be sufficient. We need to bleed off the injectors and back produce them to really keep the pressure within limits. So one of the ways is that when you develop a detailed subsurface understanding of the field, you can tell that, okay, these are the wells, these are for this duration I need to shut in, this is the minimum duration I need to shut in, sometimes 1 week, 2 weeks, 3 weeks. Some wells you see we need to shut in for a very long time, and some wells we need to bleed. So this type of things we really worked out. So in this case, really, by implementing this and developing a deep subsurface understanding of this field, we could reduce really all the incidents that we used to have while in the drilling campaign for drilling the infill wells every year. We got much under control because we developed a deep understanding of the subsurface environment and exactly which producers is injecting what injectors, and by doing the detailed calculation how long each of the injectors need to be shut in before really while drilling the zone of interest. I'm coming to really nearly the last part of the last slide. Water injection can result in elevated pore pressures Okay, then much more than what we can really predict by normal reservoir engineering like material balance and simulation studies. Sometimes people think that, okay, I have a detailed simulation model at a fine grid and I'll use this pressure for this. You can really come to grief really if you do that. Okay, so you need to be very, very careful. These elevated pressures, if you are injecting, it can be transmitted over long distances. Sometimes fracture can be pretty long, and these pore pressures can take sufficient lot of time to dissipate sometimes, as you can see from the example in this well, really, that some of the wells need to be shut in for 3 weeks, 4 weeks, months, really before that it is coming, so that my pressure really stabilizes. So we need to implement a policy of shutting in water injectors prior to drilling infill wells. Which wells need to be shut in for how minimum duration we need to be shut in, which wells I can keep on injecting without really impacting my well that I am being drilled is very, very important. This is the lessons I learned from field B. Now coming to the concluding remarks based on this 1 hour seminar. The line source of the first thing, the point I want to point out is that pore pressure prediction in a development well is a serious business. It's not that I can tell, oh, what the pressure, I just give something. This become because in subsurface, there's a lot of uncertainties, and all these uncertainties need to be taken into account. The problem becomes much more acute if you're drilling such well in a water flood environment. We can use a line source solution to differential equation of fluid flow to predict the pressure. It's very good. But whenever you use any equation, okay, there's nothing wrong with the line source solution. But the question is that you should ask, are the two assumptions of homogeneous, number one, number two, radial flow, valid? If the two points are connected by a fracture and linear flow is happening, then I can't use this line source solution at all. So it can be, line source solution can be used to find out the pressure at a proposed location in the presence of various producers and injectors, and we can also find out which are the injectors that need to be shut in and what is the duration of shutting. That's the third point is very important. Line source solution will predict pore pressure only if all the underlying assumptions are valid. And the two underlying assumptions which are critical are a homogeneous reservoir and two, radial flow. Because as soon as we have a fracture path, we are not having a radial flow, but we are having more of a linear flow. And the last point, as I told you, it is prudent to implement a strategy of shutting in water injectors prior to drilling infill wells. Prior to drilling wells in a water flooded environment, you are on the other side, you can lose some production, that is fine, but we cannot have a well process safety incident. Okay, to find out, do detailed calculation and find out for what duration each of the injectors and which of the injectors need to be shut in. So this is the topic of my presentation, totally focused on how to really do pore pressure prediction in a development setting in the presence of water injectors. I don't know if you have some time